Welcome, everybody. Welcome to NYU Abu Dhabi Institute, to this nice conference. I'm not a speaker. I'm Francesco Orneodo. I'm a professor here. And I'm going to introduce the speaker, my colleague and friend, Professor Ferroni. Sometimes, actually very often, we physicists get a question, what's the use of particle physics? Why do you do particle physics? And actually the answer is we do it because we like it and because we want to know what are the laws of the universe, how nature works. But sometimes, some very nice and powerful application comes up. And tonight, we're going to learn about one of these applications, how to cure cancer with a beam of particles. Professor Ferroni has a brilliant career in particle physics. He spent a lot of time in particle physics laboratories like Stanford in California, like CERN in Geneva, and more recently, Gran Sasso in Italy. And he's actually the president of the Italian Institute for Nuclear Physics, which is, by the way, also the institutions from which I come from. So that's all from my part. Please, Nando.
Thank you very much for this nice introduction. I am absolutely pleased to be here with you tonight. I have to make a disclaimer first. I am a physicist, and actually a physicist of what we call high energy. And high energy is produced by accelerators, particle accelerators. But this, I see it, but you don't see it. This talk has to do with things that goes much beyond physics, has to do with biology, has to do with medicine. And I cannot claim that I'm an expert in all of these disciplines. We tried it before, don't worry. I mean, it's not something that we never see. Okay. So what I'm going to tell you, I have learned much of it by being a member of the council of the foundation that ran one of these machines in Italy. So I have interaction with medical doctors that often explain me what is going on and why we have done these things. Anyhow, I will not be able to answer hard questions on the medical science, but you are free to ask, of course. I'll try my best. So the issue is that cancer is something that, due probably to the fact that we are living longer, is getting more and more important as an agent that will terminate our life sooner than we would like. This is the number of cases we have in the world, and it's an impressive number. And as you know, we have many therapies or many remedies for fighting cancer. Surgery is historically the most known, but then it comes radiotherapy, comes chemotherapy, immunotherapy at infant stage. Hadron is one alternative to radiotherapy mostly, and it's probably the only thing that can attack a few specific type of cancer. And hadron distinguishes itself in two different possibilities by using protons or using heavy ions. Heavy ions are the nuclei of one of the lighter elements that you have in nature, like carbon or oxygen or neon or something like that, helium if you want. What is the hydrotherapy? It's just, as you know, it's the T9 problem that changes when you send an SMS. It changes what you want to say. Of course, it's hadrotherapy. Unfortunately, water does not cure cancer. The physics and medicine got together very long ago when Wilhelm Röntgen, at the end of 19th century, discovered by chance X-rays. And since his wife was around, he took a radiography of his wife's hand pretty impressive what you see on the right side. And the wife was not particularly happy, and she commented, "I have seen my death." However, from that day on, medicine and physics got something to share and something to do together. The next very important step was the invention of the cyclotron. A cyclotron is a machine that, when it was invented by Orlando Lawrence, stayed in the palm of one hand. It's a very simple object that you inject. It's a strong magnetic field, and if you inject a particle on one side, and then there is an electric field which gets this particle accelerating. Since the magnetic field is fixed, this comes from the center and the spiralized outer, because the power of the magnetic field in curving it is less and less with the higher energy of the particle. At a certain point, reached a threshold energy, the particle gets out. Okay, so it's a very elegant way to get a beam of particles of a definite energy. Lawrence, of course, got a Nobel Prize because this was a fundamental discovery in our science, in particle physics. But sometimes after, another person that it's really one of the giants of physics, Bob Wilson, had a thought and say, but look, if we are able to make a beam of particles with a precise energy, then we can use one property of the particle. A particle passes through matter, okay, any matter, wood, your body, in iron, and it loses little by little its energy, okay, because it gives energy to the molecules, to the atoms of the surrounding. But at a certain point, a catastrophic effect happens. When it's at the end of its energy deposit, the last energy is deposited just in a bit of space, okay? A lot of energy is deposited in a bit of space, while normally is depositing a very low energy per unit of space. So he said, but we are able to shoot this particle with a precise energy corresponding to a precise depth into the cell of a tumor, then we kill the cell. Okay, this principle is clear. Actually, Bob Wilson was a very, very clever guy. He even designed by himself what is called the high rise, which is the main building in the Fermi National Laboratory in Chicago. So he was very eclectic in doing a lot of things. For practical use, as we will see, you need a beam of 250 mega electron volt, which means essentially it's like you put an electric field of 250 million volts. You send one particle at the beginning, at the end you will acquire the energy of 250, what you call 250 mega electron volts. Just because, to traverse the human body, this is the energy you need. With less energy, you don't get through. So the first practical machine was this cyclotron, this big, huge cyclotron made in Berkeley. And immediately after, the story goes as Ernest Orlando Lawrence's brother was a doctor, a medical doctor. So immediately asked the permission to use this machine for trying the idea of Bob Wilson. So one became the father of the particle accelerator, the brother, the father of the nuclear medicine. It's an interesting family, as you can see. Well, at the beginning, the things goes like the patient is put into, it's blocked, it's put on a bed. This is normal. You have to keep it still, and then you shoot the beam of particles into it, okay? This is the real first patient. Was taken, pictures were taken about him. This is the start of the story. Then, essentially, the proton therapy start with the cyclotron in the 50s. In the meanwhile, another type of machine was invented, the synchrotron. I'm going to explain you short what it is. And 30 years after, because the progress of science and medicine are slow, but steady. The synchrotron was set up for using carbon ions for this kind of therapy. Now, the first center in the world to use carbon ions was the Loma Linda Center in California, the South California. And at this point, of course, there is no, you don't go to somebody on the market and you say, I need a synchrotron. you need somebody that's going to build for you a synchrotron. And was the Fermi National Laboratory in US that at the time Bob Wilson was the director. So you imagine what was the pleasure in building this machine for the Loma Linda Hospital, okay? I'm going to explain better what it is. Now, of course, you don't understand why we should do these complicated things if I don't tell you what is the effect. Now, the point is, you have a tumoral cell, okay? You have to destroy it. You have to kill it. The cell has to die. Now, the practical way of killing the cell is in breaking the DNA. Now, the problem is that the DNA is pretty small. I mean, the dimension of the DNA are nanometers. So you have to precisely eat it and deposit a lot of energy. You have to cook it, essentially, a lot of energy in that small space, okay? So this is the principle. Fortunately, medical doctors tell me that the tumor cells have less repair capabilities of the normal cells. So at least at this point, you have a bonus, okay? So the trick is in sending a particle that is able to deposit a lot of energy in a small amount of space. So now, this is the energy deposit along the track of a proton, an alpha particle, that is the nucleus of a helium ion, of a helium atom, or a nucleus of carbon, okay? Now, the activity you see essentially corresponds to how much energy is deposited. Now, you clearly, and these particles are at the end of their life, are on what is called the Bragg peak, is where they leave all the energy they have in a small space. So you clearly see, and this scale is 10 nanometer, which fits essentially with the DNA strand, what you want to do. You clearly see that the carbon ions are much more effective. If the carbon ions hit the DNA, then the destruction is assured, while a proton is less effective. Does not mean that it's not effective, it's less effective. So this means, just to tell you in unit that you might not understand, but the quantity of the energy that a carbon ion can release into the 2 nanometer space of the DNA strand can be of the order of 50 electron volt. It means the energy of a proton that is accelerator of 50 volts, okay? Not much, but, you know, DNA is not so solid as we would like to, probably, or perhaps not. The standard therapy, as I told you, affirmed since long for shooting radiation on a patient affected by cancer are the photons. This is the radiotherapy that every modern hospital has got into the basement with 1, 2, or more units. Now, what is the problem? The problem is that photons are much less effective. The photons at first glance don't do anything because this is a neutral particle that goes just straight. But sometimes the neutral particle converts into electrons due to the electromagnetic field, and the electrons act as the particle that lose energy. Now, what is the problem? The problem is that what you want to do is a certain radiobiological efficiency, whatever it means, a number, which is how efficient is my particle in making the effect I want, okay? And you have to measure in units, in radiobiological unit. You cannot measure in units of particle physics because that doesn't make sense. So you see that for a certain dose, the amount of radiation that you give to the patient, well, for the same dose, this is the probability of survival of the cell. Clearly, the photons are much less effective. There is a factor 10 for the same amount of dose, okay? Or, if you like, you get the same survival efficiency with a very different dose. Now, the issue is not that the dose itself has something wrong or something nice. The problem is that that dose, if it doesn't get into the point where you want, it will be distributed in other part of the patient, okay? So the patients get the dose where the cells are perfectly healthy, and you might not want to kill them or those, okay? No, this is essentially the issue that makes the carbon ions or the protons attractive with respect to photons. The other point, you can say in other way. I mean, the photons, you cannot collimate a photon beam, okay? Photons get out and then they spread with an angle, while with the charged particles and through the help of magnets, you can send every particle to really where you want, with the precision that what you want. So this is the effect, in fact, of illuminating essentially a certain area or illuminating a spotty by the area. The effect is seen in this impressive picture, where this is a real microscope, okay, a modern one invented by Stefan Hell that got a Nobel Prize actually for this super resolved Florence microscopy. And now you see clearly that you can follow the effect of each individual charged particle that gets through the cell. And each of these dots is the energy deposit along the cell, okay? So you can precisely track what you are doing, of course not in vivo because you cannot put the microscope inside the patient, but you get an idea of what the effect of what you are doing. And this is, of course, when the beam gets into the plane of my projection, and this is when it goes along the plane of my projection. And so this is what you want, the killing of the DNA strand. Now we have to talk about technology. Now, I told you that a synchrotron was invented, and I'll show you a synchrotron after. But just to tell you what the main differences are. Okay, a cyclotron is a small machine for getting the same energy. Okay, the cyclotron is a small machine. The synchrotron is a big machine. However, the cyclotron delivers fixed energy. You cannot change the energy of a cyclotron. So you, at a certain point, if you have the energy has to be enough to get through. 250 MeV. But if the region you want to illuminate is superficial, okay, then you don't need 250 MeV, you get much less. So you need the passive degradation of this beam, okay? While a synchrotron energy can be varied, okay? So you can adjust software-wise, say, your energy. You don't need a special passive device that produce multiple scattering and other consequences which are bad. The synchrotron can operate easily switching from protons to ions, while the cyclotron has to be designed for protons. However, the cyclotron is cheaper, and there's a factor. The scale is 100 million, okay? Dollar, euro, whatever. Yen. Well, at this point, whether it's 100 million or 150 million or 75 million, so it doesn't really change. You're willing to do it or not to do it. It's another, the drive is in another place. So I told you shortly what a cyclotron is. Essentially, you inject the particles, so then the energy is increased by an electric field, so the trajectory gets higher, gets looser and looser, and then the particle gets out. A synchrotron is a completely different object. You inject the particles, but then you can adjust the magnetic field. You can change, these are all the magnets that keeps the electrons or the protons in orbit, and you can adjust in real time that field. So you can increase the energy, but staying always in the same trajectory, because you increase the power, the bending power of the magnets. Okay. So this is the advantage. Now, I told you about passive degradation. If you have a cyclotron, the beam comes out, but then, according to where it gets to get into the patient, you have to have modulate and shift the energy. So you need a lot of stuff in between the outcome of the accelerator and the patient, okay? Also because what you want to give is not a dose in a single point, because you cannot change the energy easily with this machine. You want to spread the dose into the volume, say, of the tumor. Unfortunately, there's a point that the tumor is not a cube, okay? So, so this, at least you cannot command it to be a cube. While with a synchrotron, it's extremely easy, because you just change the energy in the machine, and then you direct the beam where you want with the magnets that scan, or it can scan horizontally or vertically, okay? So essentially what you do, you paint, in jargon it said, you paint the tumor. Okay, so I told you the difference between photons and the protons, so I don't need to spend time. I want you to look a bit at this transparency, because as you see, suppose this is the Bragg peak, okay, the point where carbon ions deposit all the energy they have, okay? And suppose this is the amount of energy you need to have the effect. Now, if you use photons, which are this green or yellow, it doesn't matter, object, you see that the photons have an effect from the beginning. When they arrive at the point where you want, which is, for example, 25 centimeters deep inside, we are water, so water equivalent or water or human body is the same thing. They have lost most of the effect. So you have to raise the dose. This is the explanation. You have to raise the dose to put this area up here, but then this one goes up here. Okay, so essentially you give more dose. The advantage of a synchrotron is the absolute position control, because not only you have the scanning system, but of course you have these detectors, which are completely mutated by the experiment we do in high energy physics, which track particle by particle the exact position and give you the feedback where you are going. And so essentially what you do is these things, that once you have identified the tumor through a PET scan or a CAT or whatever, then you know precisely where it is. So you just patiently go slice by slice, killing the cells at each individual depth, okay? So the advantage of hadrons is precision, definitely, okay? So you get what the medical doctors call conformal irradiation of tumor volume, which in my language is reduced damages to healthy tissues, okay? Well, so precise painting, which is obtained by the convolution of many of the Bragg's peak that you obtain changing the energy of the synchrotron. Well, this is an example of what you do. Now, X-rays, the radiotherapy, is done with beams that are not a single one. I mean, are 7 or 9 beams that point to the tumor. This is the effect in dose, okay? The dose red is the maximum dose, and white is 0. So you see that the tumor is supposed to be the red area, and the red area is illuminated perfectly, okay? So it gets the dose you want. However, you see that you spread the dose all around, while with the protons, at least you spread the dose only in the direction where they are coming from, but not everywhere, because here they stop, okay? So there is no way to bring damage to here or here or here. In few specific cases, pediatric patient, there are tumors that are probably terrible things to discuss with, where you have to send the beam up from here, okay, to illuminate a part of the brain, and then with essentially this is a photon. This is the dose you get with photons. This is the dose you get with protons, and this is the difference, okay? This minus this. And you see that essentially you give those to other parts of the body. If this is above threshold for causing a secondary tumor, forget that. I mean, I don't think even we have enough statistics to understand these things. But certainly, If I were the patient, I would prefer not to get it, okay? But possibly I'm wrong. There are more than 40 centers that use protons for hadron therapy around the world. 14 in USA, 12 in Europe, 8 in Japan, and a few somewhere else. There are 6 centers with carbon ions, 3 in Japan, 2 in Europe, 1 is in Germany and 1 is in Italy, and 1 is in China. Then there are dual centers that can do both. However, doing both is a pain in the neck for question of switching the sources and other things. You lose time, which is not what you want to do. You want to cure more patients that you can in the life cycle of the machine. But the interesting thing is that 27 new centers are planned. The US that started the game, stopped the game at a certain point for a very long time. Now they have, under the advice of a panel of National Health Institute, they have decided to restart the things, and they are planning a lot of centers. The first one will be on carbon ions at Dallas University in Texas. So far, more than 100,000 patients have been treated with protons. More than 10,000 patients have been treated with carbon ions. As you see, most of them have been treated in the last years, so the thing is increasing. And now the rate is 10,000 patients per year. Funny enough, you see that, I mean, this is the number of patients versus time, and it's clear that we are on exponential growth. So the business, let's call business, okay? The funny thing, no, it's not so funny, but that all the centers are essentially in the north of the world, okay? Recently, I went to Brazil to try to convince them to have one. I mean, Brazil is a rich country, and so on. And effectively, they said, but this is impressive. Why should you do? Australia is another case why they shouldn't do. But everybody can do it. I mean, it's a matter of understanding the advantage from many points of view that I might discuss later. Now, why should, I mean, as I told you, however, the goal is to solve the problem of a patient. If you solve the problem of a patient with radiotherapy that costs less, fine. I mean, that should be fine. However, medical doctors tell me that there are few tumors that you cannot do with radiotherapy. There are chordoma, chondrosarcoma. Oh, these numbers applies to Italy. Italy is a country of 60 million people, okay? So now you can scale. Chondrosarcoma, eye melanoma. Eye melanoma, for example, is the most intriguing case. I mean, eye melanoma is in the surface of the eye. So if you do photons, you just illuminate the brain. Again, perhaps it works. No, I mean, nobody tries to cure eye melanoma with photons, okay? Eye melanoma is for protons. This activity started in Italy long ago in a research center of INFN, and then now is given to specialized center. And the other case is pediatric solid tumors, okay, where essentially you should do with protons. So the numbers say that we should have there are 1,000 cases per year in Italy that should be treated with protons. And if you could do 14,000, that would be better for the life of the patient. Carbon ions is, again, another kind of thing. So there are head and neck tumors, some kind of carcinoma, soft tissue and bone sarcoma. There are cases of prostate, liver, and pancreas that if you select a case, you could apply it, okay? And I remind you that liver and pancreas are not nice type of cancers. So again, they say that 15,000 per year, 1,500 per year should be done with carbon ions. Of course, you can do more, but I mean, this is what you need if you want to try to give a chance to these people. So there are clinical indications now established in the book. You can read yourself. And again, the key word with carbon ions is the fact that they are able to deliver much more dose in the small space. So there is a lot of a lot of medical arguments for favoring, in a few cases, the carbon ions. I'm not able to go into the detail, but I leave you for consideration. The first center making use of the carbon ions, again, when therapy restarted after Berkeley gave up, was the HIMAC center in Japan, where they have 2 identical synchrotrons. Now, read this. They can use any type of ion. However, for lack of enough research, for lack of the fact that you want to cure a patient and not to do research, the therapy so far is essentially confined to carbon. It's a point that I'll come back on that. Okay, this is the type of pathology they have attacked with this machine at IMAC in Japan. This is the Italian center, brand new, that we started a few years ago to construct with the help of INFN. Actually, INFN has built the machine, and there is a foundation, a medical hospital that is running it. Patients are coming after the test phase since 1 year into normal things. This is a synchrotron. Okay, this is the problem. It's a 25 meters diameter object. That's it. I mean, it's not something that you buy. You can, with help of a research institute, you can do it. Okay, many research institutes in Europe or US will be willing, of course, to help. I mean, in Europe there is INFN, there is GSI, there are CEA, and in US there is Fermilab. So this in getting it is eventually it's easy, but you have but you cannot sign an order to somebody. Okay, you have to negotiate with somebody and understand how to do. There is the problem of training the people and other stuff. Okay, schematics. It's simple. So this is essentially what you see. I mean, this is a cyclotron sides. This is a proton machine sides for the same energy. This is an ion machine sides. Of course, patients are treated according to the best way of surveying, positioning, and monitoring what you are doing. So this whole of treatment are pretty science fiction. Of course, told by somebody that's not tried, but if you try, probably you have a different opinion. What are the new challenges? Okay, now imagine, so far I have told you about cases which have to do with the head. Head is very simple. You put the patient on the bed, you put a mask, you screw the mask on the bed, and you cannot move. Okay, so you precisely know what you're doing. Suppose you want to do another part of the body that is subject to respiration, breathing. What you do? I mean, the beam continues to get to the same point, but the target is moving. Okay, so now there are 2 ways, essentially. One is to follow with some infrared or whatever monitor that you put on the patient, the movement, and you activate the beam only when the patient is in the position which you say 0 position. Okay, this is a waste of beam because in a cycle you can use the beam only for a little period of time. So you would like to do much better. Okay, this is you see, this is what happened. Okay. But now, of course, if you have if you have a very precise description, okay, of what the movement is, and that you can get because, after all, you can do a PET scan in live time, so you essentially have a description of what you're doing. Then you say simulate this effect and introduce this effect in the operation of the machine. So the machine will change the energy and the direction according to where the sensor says that the patient is in that moment. This is clearly at the frontier of what the centers are doing. I mean, it's halfway testing and operation. I think it's operation by now, but okay. Okay, so the motion compensation is an extremely important issue. The point is how much time a patient has to stay on that bed, because that determines how many patients you can cure per day, okay? Now, it's true that the preparation time of the patient is much longer than the actual irradiation time. Irradiation time is of the order of 1 minute, okay? And the patient, it takes 20 minutes, essentially, to set up and monitor and precisely set up the patient. However, if you start to use only a fraction of the time, then the 2 times becomes comparable, and then you are losing patients. I mean, you cannot cure. The target of this machine with 3 treatment all is to have at least no less than 1,000 patients per year, not 100,000, 1,000 patients per year. So, but it copes also with the number of the cases you have absolutely to do this way. There are 2 potentialities that are being discussed into the community now. One is pancreas. Okay, pancreas is a killer. There's nothing we know I mean, to solve this problem. When you are diagnosed with pancreatic cancer, then you start to write your last willing, essentially. Well, because it's in an impossible place, essentially, because it moves, because surgery doesn't get into, because surgery does more damage than shorten probably your life for what short can be. But it has been tried. Okay, it's been tried with a combination of carbon ion therapy and gemcitabine, which is chemotherapy, essentially. Now, certainly, the number of patients is not 100,000. Okay, the number of patients is small. But the survival rate at 1 year and at 2 years with this way are essentially indicating, especially the one at 2 years, that there might be hope and a chance for this therapy. Okay. One of the important issues is that there are only, as I told you, few centers in the world that can do it, and these centers have to cure patients that are for which you know that you have to do it. Okay, so there is a little time for research. One of the important things, hope for the future, is if you have more and more centers, you can have more time for research. You can expand the range of action of this machine. The second issue, and this is really a dream, but people are thinking to it, is that the cardiac arrhythmia. Okay, cardiac arrhythmia, people tell me that it's a very bad object, that it's very difficult to treat. It's a painful intervention, and the success rate is not 99%. And there are complications in few cases. Now, the problem is that you have to isolate electrically one vein inside the heart. That's the issue. So if you could do it by carbon ions, that would be great. I mean, you don't have to put your bisturi, your knife, inside the heart of this poor guy. However, this is a 5-dimensional problem, because the heart does like that, and at the same time you breathe. So, I mean, here, and the vein is small. So here, and you don't want to irradiate the other parts of the heart. So it's an interesting and challenging problem. So again, of course, you make research, but it's in the future. Everybody would be using probably this therapy if this machine would be as small as this platform and as cheap as a few millions, right? Unfortunately, I'm talking about something that is 20 meters, and it costs 100 millions. Well, it's not a reason to stop, because I think that 100 millions that have a double marker. One is for the life of your citizens, and the second is for research, for a progress in the possibilities of solving other cases are well spent. But still, I mean, research goes into trying to do better, cheaper, and smaller. There is not an easy solution to it, okay? There are few ideas. Gradient field acceleration, dielectric wall accelerator, which are LINAC essentially. But a LINAC would be even a more flexible machine than a synchrotron, but unfortunately we are not able to produce more than 30 mega electron volt per meter. So to get to 250, given all the spaces, eventually you end up with 15 meters of LINAC. So it's not that we are changing the scale of the problem by 1 order of magnitude. The real dream is the plasma wave acceleration, okay? It's a very difficult subject, but it's the most fascinating one. You have a gas, and the gas is made by atoms that are loosely moving inside. Now, you inject a lot of energy in that small window, 100 microns, 1 millimeter. You pump a lot of energy with a logic. So you create a plasma. A plasma is an object where nuclei and electrons separate, okay? It becomes a gas, not of atoms, but a gas of nuclei and electrons. So now, if you convince them, all the nucleus to go on one side, all the electrons go to the other side, then when you inject a proton, the proton is sucked by the electrons, okay? But because it's an extremely high electric field, an electric field that you can create on the atomic scale, it's infinitely huge with respect to what you are used to, okay? And then you could have an object which is as small as this platform and gives you the energy. There are two problems. One is how to induce the precise plasma field. That can be done easily with a power laser, but power means hundreds of terawatts or petawatt. At this point, this laser exists, but as big as the room from there to there, it doesn't matter. In 10 years from now, these lasers will be as compact as this, okay? No point. And the second problem is that the precision on creating this plasma is not such that all the particles get out with the same energy. I mean, the particles get out with a bit more energy, a lot of more energy, some average energy. So, but you need a precise energy. So you have to understand how to combine these two things. I don't promise anything. Come back in 10 years, or participate in the research, and then 10 years from now, I think, or in 20 years from now, we might have the motor of the knowledge is the fate that is the future. Right? You never give up on that. So, the future of particle therapy, to my view, strongly depends on the application of nuclear physics. It's nuclear physics actually that's driving all this research. We are not doing it primarily for doing it. We need accelerator with higher field, so this will do no matter what. Okay. Moving target, we have to understand better how to control the movements, how to combine the energy with the movement of the patient. So online beam monitors, exercising and researching on new diseases. There is an entire field open. The combination of treatments, how immunotherapy with carbon ion or immunotherapy with, but you have to have machines to do it. You have to have time to do it. You have to have a lot of people, a lot of medical doctors and biologists in doing it. Otherwise, we cannot, the progresses cannot be made. And having one of these machines, it's an extraordinary asset, because what I didn't tell you is that, of course, you are curing patients, but you might always have another line, okay? Another line that provides you these particles, carbon ions or protons, not for using patients, for doing research, on which you do research on in vitro and in vivo. You can use little animals, you can use cells. There you can exercise, and then since the patients are not usually cured at 3 a.m. in the morning, nothing prevents you to change the source, and you switch at 3 a.m. in the morning the source for carbon ions to neon atoms, or argon, and so, or helium, and you understand what are the differences, of course, on animals or in vitro first. So you have a degree of an additional degree of freedom so to do a lot of research on this. But this research has to be done together by chemists, by engineers, by biologists, by medical doctors, by the physicists that adjust the parameters to the machine. I think it's important, but to me the most important thing is that to demonstrate, and I think has been demonstrated, that this is an important tool for saving lives. Thank you very much.
Working here in Cleveland Clinic, Abu Dhabi. And to be honest, I want to confess that I was very conflicted tonight because it's Thursday, it's weekend from tomorrow, very tired after 1 week, and said, should I go or not? And say, okay, let me to go, but I'm sure that I will not understand any words, and after 5 minutes, I will leave, and that's all. Now, I would say that maybe if you can keep going and speak another 1 hour or 2, I will stay here just to listen to you.
No, I mean...
Because, yeah, it's very different, it's very difficult talk for me, but what I can realize is that really we have an incredible progress in science. As a surgeon, my teacher always said, nothing can replace surgery. There is not the best chemotherapy agent, the best radiotherapy that can replace surgery. Today, my question for you is this still true, that nothing can replace surgery? Or maybe in the future, not tomorrow, but in 10 years, this new treatment can replace surgery? Or we should always work in combination, that this is treatment, as your last sentence is, will replace X-rays, will replace radiotherapy. So we can work together, physics with the surgeons, biologists with caregivers and physicians. Look, so how long should we wait for?
After all, I don't think that surgery is such a bad thing. I mean, I tried once, not for a cancer, but I mean, if you can eliminate a tumor with a very high efficiency, with a surgical intervention, I don't see really any problem. Okay, I mean, after all, you might have even less complication. Okay, I mean, any time you irradiate a person, you do something, however, on cells that you didn't want to touch in principle, right? So one of the issues for the future I mentioned is radiosurgery, okay? If you imagine how to precisely, I mean, contour the things. I'm not a medical doctor, okay? I would like to see this planet, I mean, without people dying by cancer, okay? So whatever works, it's fine with me, okay? Now, we are at the stage of adding weapons, okay, to fight this disease. We are not at the stage of probably of saying this is a final weapon. So I don't think that on the scale of 20 years or say my lifetime, one of these things will disappear, okay? Not even the radiotherapy will disappear, probably, just because in 20 years we might be at the point that this machine can be placed in all the hospitals of the world, okay? While in this moment you have to think at a very big hospital, I mean, a hospital which also have research activities and things like that, because it is an investment after all. No, but I think that for a terrible disease like that, having more weapons is better than anything else. To you, I mean, to your colleagues, is to define which are the best cases of application. And then when, as I told you, the combination of methods has not been tried, essentially, really. Even with 10,000 patients are not enough, I mean, for understanding what you're doing. We need to build 20 more centers of this type, okay, in countries where you want to also are able to do research. And then we might start to optimize things. Thanks for the things at the beginning, but since you are Italian, I don't count them as...
Could you go back to the slide that had the 3 institutes for carbon-based being started in Japan, and I think 27 new protons? I don't understand why is certain countries using carbons and why are certain countries using proton. Could you explain that?
Well, it's like, you know, you might be familiar with the hospitals. Many hospitals in the world now have this cyclotron to produce radioisotopes. These are machines as big as this platform, okay? You have a technician that just turn a knob, and at the end in the morning, the radiochemicals come and they make some tests, and then you ship these things everywhere. A cyclotron is much simpler to operate. A cyclotron doesn't do ions, but also a cyclotron you buy, you just go to Varian or to IBA company, you place a check of, I don't know, 100 million, 80 million. They come, they provide you operators, they certification, everything. With the ions, we are at the stage of building machine in collaboration between with foundation, hospitals, or whatever, and the research institution. It's not the same thing, clearly. So you might want to have carbon ions, but you might not be able to afford it, okay, on a large scale at this point.
I have a quick question about numbers and cost. I know the fixed cost is high, let's say 120 million euro. The cost for the patient, depending on the tumor,
okay,
it can be, I know, 20, 25,000 euro for the patient.
Perfect.
I know this.
Perfect.
So, and I know the business case is if you have 1,000 per year, that's 25 million revenue per year.
Which serves to run the show,
Exactly.
but not to repay the machine.
I know, not just the machine, also the staff,
yes,
the cost of hiring people.
Yeah.
Besides more centers being built, what can be done to reduce the cost? Because after 5-6 years, why should the center still charge 20, 25,000 euro when the fixed cost has been covered already?
Okay.
You know?
The point is that your arithmetics is slightly wrong. 24,000 euro is what is charged to the national health system in Italy for curing one patient. And the basis is 1,000 patients, which makes 24 millions, which is what the center spends in 1 year for having the staff, for the consumables, for the changing parts, for running the show, not repaying the... Of course, this has been done, I mean, the center in Italy has been done with the money of the government, okay? So the government gave up the idea of getting back the investment. In US, where you want to get back the investment, the cost of a patient is $100,000. And then you get the money back, eventually, okay? One advantage of these centers is the lifetime of this accelerator can be 50 years, okay? The accelerator will stay there. All the surrounding parts, I mean, you can improve, the other parts you can change. I mean, if you have a better system to scan, a better system those parts are soft in a sense, you can change. The source of the particles will be always there, okay, to serve you. This is the meaning of the investment.
The pancreatic cancer, you had a 74% survival rate at 12 months, 44% at 24 months.
That was pancreas, right?
I think so.
Yeah, pancreas.
That was in 2008. Do you have their 5-year survival rate, or can you predict what you think it would be?
No, prediction is impossible. I mean, I think that prediction is something that you do in physics, but not in medicine, okay? I can find... okay, these one are new. The one below are new. Okay, the data from 2008 are relative to therapies which didn't include the carbon ions. Okay, so for carbon ions, more than 24 months, you cannot do it because the last part, I mean, these patients have now, the time is 24 months has passed since the particles were delivered. I think that, again, and then the number is 35, it's not 100, it's not 1,000. But again, here, the point is that you do not have enough places and enough time to test these things. Because you have to choose to spend 5 hours for studying the problem of pancreas, while in these 5 hours you can treat many patients with eye melanoma. And you know that those patients with eye melanoma, it's essentially 100% probability of success. Okay, there's no point. So probably you better, I don't know, I mean, it's an ethical problem, I'm sorry. I get into a field that I'm not able to deal properly with. But essentially, if you would have many more centers,
One more.
and then you could do, probably you could do even at night these cases, I mean, but you have to set up a mechanism, okay? You have to, something, this is not routine, okay? Carbon ions is not routine. It's still something that it's half a way.